Alright, so I thought, with all of my objections to the way that arithmetic has been formalized conventionally, and really just numbers and all of that have been formalized, I thought maybe I would start working towards something of my own. So here, there's a little bit of an intersection with classical notions, but yeah, I'm not using things like Peano's axioms and shit like that. So, a set, start off with a set, and that is a noun. I'm indicating when things are nouns and verbs. I'll probably increment. I might have got that wrong. Yeah, there it is as a noun. So yeah, definitely not done with this work, but anyway, a set is collection of features. So it's like it's a logical thing, a cognitive thing, perhaps. And a member of a set is an indivisible sample of that set, right? So this is, the set will identify and I guess include. Perhaps I haven't thought this through thoroughly enough, but sort of like a classical set of something. The members have features, they have qualities, and a member is something, a sample of the set, that it's a whole, complete part of that set, right, that you can separate off. But that part cannot be separated further. It cannot be divided up into other pieces. All right, so like a subset classically is probably in general going to have multiple members in it, right? So that's a divisible sample of the set. A member is an indivisible sample, right? So it's an individual member. But I'm trying to, before we've explained numbers, I can't really use things like individual 1A. I can't use these words because they don't make sense yet. If I use them here, then that would be cheating. Okay, so a unit. Now this one has two senses, I think. There's a concrete sense and an abstract sense. So and they're both nouns. The concrete sense is an identified set member. And the abstract sense would be like a schema for identifying the set member. So this is really closely aligned with the features that define the set. That's going to be more or less the schema of a unit of the set. So to do this, you identify if something fits within a given set, and then you identify if it is indivisible. Right. So in order to get a unit, you have to tell whether it belongs to the category that we're thinking of the set, and if it is an individual of the set. It is indivisible. It is not some collection of members of the set, right? It's just one. Right? 0 is a noun, and that is a lack of units. There's nothing. Okay. This, I feel like, is different than an empty set. I feel like that is a mistake in the way that it's normally thought of. 1 is presence of a unit. So that's all you got. You've pulled an indivisible sample from the set, and that's 1. That guy right there. That's 1. Incrementation. So here we are gathering identified units together as each one is identified, right? So we don't just take the set as a whole or some subset as a whole. We pull off members one by one. And as we do that, the group that we end up with is incremented. Okay? And an increment is increase a unit gathering by 1. A number. This is a concept that I think we have to highlight here. This is a noun, and it is the size of increase of a unit gathering from 0. So, as we gather up this group, which started off at 0, it always starts with nothing. We always start counting at 0. The number of units is the size of this group. Okay, and conventionally we will name numbers for the sake of convenience. So 0 is the lack of units. That's where you start. 1 is the presence of a unit. So that is these two things, 0 and 1, in many regards are not numbers, because they are more fundamental than numbers, far more fundamental. And I think this is also a mistake that is made classically, where they try to just write off 0 and 1 as random ass members of the set of natural numbers, and then they're surprised that shit fails. Yeah, 0 and 1 are absolutely special. Unambiguously, definitely for sure, 0 and 1 are special. So not treating them as special is a mistake, I think. And then we get the other numbers. So 2 is the result of incrementation from 1. 3 is the result of incrementation from 2. 4 is the result of incrementation from 3. 5 is the result of incrementation from 4. 6 is the result of incrementation from 5. 7 is the result of incrementation from 6. 8 is the result of incrementation from 7. 9 is the result of incrementation from 8. 10 is the result of incrementation from 9. 11 is the result of incrementation from 10. 12 is the result of incrementation from 11. And then at this point, English number names become formulaic, with only occasional new number names appearing, with the next number name that's really distinct being 100. And that's quite a ways out. I'm not going to write that. 13, 14, 15, 16, 17, 18, 19 are all formulaic, although in a backwards way from 21, 22. Well, I guess 20 is... It's also formulaic, but in a weird way. Meh. Yeah, so 20, 30, 40, 50. Those are formulaic. The 10, so it's like 2 10s. 2t, 20, 30, 40, 50. Right, that's literally what's happening. But whatever. It's formulaic enough. Fuck it. Okay, so count is a verb. And this is stepping through the list of number names while incrementing. Right? So in order to count something, you have to step through this list that we have. So it's important that the list exists. Right? We have to fabricate the list. And it has to be explicitly fabricated. We have to, even when we get to the point where the names are formulaic, we have to know the formula. We have to be able to step through the number names in order to count. This is very, very important, and it is not a part of the classical analysis. And I think this is a very, very fundamental issue, because you cannot count if you don't know where the fuck you are. How do you count from 1,000 if you don't know that you're at 1,000? Like, you have to have the names. You have to be able to look up where you're at and where you're going. This is non-negotiable. And now we can get into the so-called operations beyond incrementation. So here, and you can see that these all actually utilize incrementation while also being iterated versions of the level previous to it. So addition is iterated incrementation, but it also utilizes incrementation. So like all of these, we have 2 columns occurring, right? This isn't necessarily the only way to think of this, but it's the only way I could think of on short notice that has the same appearance, the same basic form for all of these operations. So, like I said, this is definitely a preliminary work, so I might be changing things. But this is where we're at right now. So add is a verb. Here we simultaneously count to the first number, and starting at the second number, we increment with each incrementation of the first number. Addition is the nominal form of add, and sum is the result of addition. So we can have a sentence like, the sum of 2 and 3 is 5, and that is demonstrated with, here in the first column, we are incrementing from 0 up to the first number, which is 2. And then in the second column, we are incrementing from the second number, which is 3, up to the point where we reach 2 in the first hand. So 0 yields 3. As we increment that to 1, and that yields 4. And then we increment the 1 to 2, and that yields a 5. And now because we've reached 2, which was our first number, we stop, and thus our result is obtained. So our answer is 5. Our sum is 5. Multiplication, it's very, very similar. So here we simultaneously count to the first number. And starting at 0, we add the second number with each incrementation of the first number. Okay? Multiplication is the noun form, and the product is the result of multiplication. So the product of 2 and 3 is 6. So starting at 0, on the one hand, counting up to the first number, which is 2, we will add 3 with each increment. Okay? So 0 yields 0, 1 yields 3, and 2 yields 6, and then we stop, so our result is obtained. Thus, 2 times 3, or the product of 2 and 3, is indeed 6. That's your product right there. Exponentiation, exponentiate being the verb, exponentiation being the nominal form. As far as I can tell, there are not nice words anymore for these things. This is probably reflected in the fact that classically arithmetic really just went to here, just to multiplication. And I think that's a problem. We should be able to naturally expand it with really no effort. If we've set up addition and multiplication correctly, we should be able to naturally get subtraction, division, exponentiation, logarithms, tetration, all of, everything from here out naturally, very easily, just by simply iterating on the previous step. And classically, I don't think that's really achievable. Multiplication, the rules that are set up for it in the P&O arithmetic are they don't look the same as the addition rules. Unlike what I've done here, it looks different. It looks awkwardly different. All right, so we're at exponentiation. Okay, so exponentiate is the verb, and here we will simultaneously count to the second number, which is the small number, when you are writing it out, the power, and starting at 1. So previously we started at 0. Here we're going to start at 1. We multiply by the first number, which will be the base, with each incrementation of the second number, which is the power. Or the exponent. Exponentiation is the nominal form, and the power is the result of exponentiation, which is confusing because you can also call the exponent the power. So this is clearly an area where we are confused about things culturally. It is unambiguous. It is definitely true. We are confused about what the hell we're doing at this point. And we're really not that far in. That's kind of pathetic that we're confused at this point. Anyway, so 2 raised to the power of 3 is 8. Okay, so our incrementation column is going to 3 now, because we are, unlike here up above, we are counting to the second number, not the first number. And starting at 1, we are multiplying by the first number. So our second column, instead of starting at 0 like it did here, we are going to start at 1. And our starting point is different here because with addition we start with our second number. With multiplication we start at 0, and with exponentiation we start at 1. So it is apparently normal for your starting point to bounce around at least a little bit in these first stages. Okay, so 2 raised to the power of 3 is 8. So incrementing or counting up to 3, we are going to, starting with 1, multiply by 2 at each step. So 0 yields 1. That is our starting point. Counting to 1, we get 2. Counting to 2, we get 4. Counting to 3, we get 8. Now we have reached our second number, which is 3, so we stop. And thus the result is obtained, and the power of 2 to the third is 8. And there you go. And I think from this, one, it's cleaner and simpler. I don't know if it works perfectly, but I also think it works better. Because we are now talking about what units are, how we're identifying what a unit is, how we're identifying what 1 is, and we are consistently, because we have defined a unit, we are clearly defining that 1 and 2 are distinct things as long as we're holding to a unit. And this is actually going to serve as a formal proof that when your units are commensurate, 1 plus 1 actually is 2. And this is a job that was never done with P&O arithmetic. And this is why Whitehead and Russell were incapable of actually demonstrating it successfully. And I think this might be a large part of the problem with the arithmetic system that Kurt Gödel looked at and found problems with. That's not to say that I think that this won't have problems and cannot also, that this doesn't necessarily share the incompleteness problem. But I strongly suspect that all of those issues were a major factor in making it relatively easy to detect. Not that Kurt Gödel was a badass by all accounts. Very hard worker. So that not that it was easy to detect and figure it out, but hopefully, hopefully this makes things a little bit better, or at least this line of investigation of it. I'm pretty sure this is going to clean up something. Yeah, at any rate, that's where I'm at. And that's, you can tell by what I'm saying, where my head's at on this. And, I have absolutely no problem being wrong about this and discovering that this is complete shite. Because that also teaches me things. So